Good morning and welcome to the COEE website. Last time we talked, I showed you the prototype board I was working on for the WWVB receiver. Well, this time I've pretty much got everything done for the WWVB receiver. I've laid out a board. I've gotten the schematic all done. I've got my bill of materials. It's basically ready to go to production run. And in the production run, I don't know that all this stuff is going to work. So I want to get the production run in, maybe 2 or 3 samples, something like that, to be able to really produce this board and really find out what I need to change so I can produce this board. Are things working well? Are things not working well? Those are the sorts of questions that I want to answer. So let's go ahead and get started. The schematic itself really hasn't changed too much, so I won't go into real deep details on it. So here's the first JFET stage. I have added a low side FET to turn on and off this stage. This will help in a couple of different areas, but primarily with not having it draw too much power. Don't want it drawing any power at all. So when I turn this on, this node will essentially be ground. And then when I turn it off, this node will not be pulling any current, so this node will go up to the 5-volt rail, which essentially makes this not pull any current. And then there's the second stage. It hasn't changed a lick, other than I've used an op amp with a shutdown mode on it. The third stage hasn't changed a whole lot either. It still has a 100K trim pot. It's a digital trim pot, so I can adjust the gain so that there's enough gain here to be able to turn on and off the comparator inside the microcontroller. And then I have changed this to be referenced to that kind of mid voltage point. I did choose another part to have a mid voltage point. Again, it has shut down, so everything really in this circuit has shut down except for the digipot. Well, the digipot doesn't have shutdown, but it is very low power when it's not communicating. So this is going to be an excellent solution for very low power applications. So the last thing I'd like to talk about in the design changes I made from last time is that I spent a lot of time choosing what microcontroller to use. I knew I wanted to use the MSP430, but there were a couple of different booster packs that I wanted to be able to interface this with. And which launch pad do I want to use and stuff like that. And this is the one I'm planning on using. We'll talk about it in a second. But this series is excellent for doing all sorts of FRAM sort of thing. If you need a lot of non-volatile, FRAM is awesome for that sort of application. And I have used a lot of FRAM before. So, and then they even have a cheaper grouping somewhere here. Oh, I can't find it. Maybe they've stopped producing this even cheaper ones. But, oh no, this is their bottom dollar one right here. And this is what everybody starts in. A lot of times in college, if you're a college student, you've probably used this, or maybe an Arduino or something like that. I really like the MSP430s a lot better than Arduinos for a lot of reasons. But, I mean, $10, you cannot beat this price. And it's really an excellent, excellent learning and developing tool. So, really, I encourage you to get this. It's awesome. And I've got this one, which is an even lower power one with FRAM. This is really the bee's knees when it really comes to a lot of microcontroller applications. This part is really, really a good part. There's a lot of space. You have smaller versions with less space. It's a great little part. Anyway, so we'll be using the FR6989, and it's also a great part. It's a bigger part, than I typically like to use, but you know what? This is a great thing for hobbyists and home sort of work, so it's an excellent tool. And so here it is a little bit more close up, and you can see that it has a microcontroller, has a few buttons on it, has some auxiliary power that you can provide to other things in the 3-pin format. It has 40 input and output pins. You can saw this off right here with like a hacksaw or whatever, and use this to actually program your production run stuff if you want to, where you have this microcontroller on your production run stuff. You can actually use jumpers and stuff and still use this little board in developing your production stuff, or even programming your production stuff if you figure out a good way to connect this board to your own board, to be able to quickly program it, which is an excellent technique and idea, and I've used it myself. So, you know, just kind of keep these things in mind when you're going into production. Here's a different view of it. So and this thing has the energy trace, which I really like, which also looks at how much energy's being used throughout your state machine cycles. So when it turns on, how much power does it take after it's turned on? And then when it's turned off, how much power is it taking? And it has very good application in the Code Composer Studio to be able to do that. There's also this connector here, which I don't know a whole lot about, so I'm not going to speak too much about it, but it's something I'm going to play with on the side. And it's supposed to be able to do some motor control and stuff like that. So anyway, take that for a grain of salt. So I spent a lot of time thinking about where this product could possibly be used, and some of the bigger things I thought about was in an Internet of Things sort of periphery, where you really wanted to get world time without connecting to the internet of some sort, get actual time and sync up all your devices. So I thought, well, if you're going to sync up all your devices, you're probably going to want a Bluetooth connection. You're probably going to want a Wi-Fi connection. So there's a Wi-Fi module and a Wi-Fi booster pack and this Bluetooth. And I wanted you to be able to use any one of these things to connect to this and to my prototype board. So what I did was I thought, well, okay, we can put all these three. TI has this awesome booster pack checker sort of thing. And let's see. And so these are the pins that it would use. So any of these black pins I can use. There's a couple of them that are shared, like the SPI clock, and then there's also SPI slave out, master in, and slave in, master out. I've never really heard it called that. It's usually master out, slave in, or master in, slave out. So I call them Miso or Mosey, but they've got it backwards here for whatever reason. Okay, so that's kind of where I was going with this, was that, you know, these are the pins I can use in my design. And fortunately, I was able to figure out ways to connect to just those pins. That way you can use any one of these booster packs connected with my booster pack and this particular MSP430 to give you what you need. One thing I was going to point out on this, of course, is that it has an LCD screen. That LCD screen, let's see, let's look down here. Oh, there it was. Actually has a clock on it, and that is one of the reasons I chose this particular booster pack, is it has this clock here, and I can also show that it's receiving the data properly, and so this is an excellent way to do this. Alright, so now let's go look at the board a little bit. I had started out designing this as a 4-layer board, and as I looked more and more at the 4-layer board, this is going to be a pretty large board. It's about 6 square inches, and that makes it a pretty expensive board to produce, so I wanted to bring it down to 2-layer board. And when I did that, that reduces the cost of where I'm going to go to buy the board by about half. I'm going to use Osh Park, and we'll talk about them in another video probably. But I wanted to just build this board and get it going, but I wanted it to be on 2 layers to save myself some costs, both in all the way around. If you can make it a 2-layer board, it saves you costs, period. The less layers you use, the more it saves you. Now there's applications where you can't use a 4-layer board, or a 2-layer board, in just about every microcontroller application I've ever done that needs serious interfacing with this sort of stuff. I've had to make it a 4-layer board always. I've never had to go to a 6-layer board, although that's been something I've considered once or twice. But going to 6-layer boards, because 2-layer and 4-layer boards are the most standard boards you'll design. So jump into a 6-layer board, it increases the cost pretty significantly. So you want to do a 2 or a 4-layer board, but a 2-layer board and a 4-layer board are pretty much standard. Only time you're going to see more than that is like in medical applications, aerospace, high-end sort of stuff. And what I've typically done over the last couple of years anyways, not high-end stuff, I have designed a 22 or 24 layer board. I forget exactly how many layers it ended up being, but that was for an aerospace application, and it was very large and very big, and so I'm trying to stay away. Well, it was a lot of fun to design. We'll talk about it some other time. Let's see. So let's zoom in here a little bit. Let's see if we can get most of it. There we go. Perfect. All right. So notice that I've divided this up into basically, let's see, 5 segments. Here's stage 1, my single point ground that we talked about last time. Stage 2, stage 3, my voltage reference, and then there's some periphery stuff over here on the edges and stuff, which I could probably delete these lines. They're still kind of part of stage 3, but and maybe I'll do that. I'm not quite done and ready to produce this yet, so maybe I'll still take those lines out. Anyway, so this is a really good board if you ask me. I mean, of course I'm biased, but here's the first stage. I mean, it is tight. I laid this down and I did not change it. There was no changes. I just laid it on the board and it looked great. So there you go, really. I mean, I thought it was perfect. And so I haven't changed it. From the 4-layer board to the 2-layer board, I have not changed it. If we zoom in here on the second stage, it's laid out really nice. It's nice and tight. The positive and negative inputs are laid really, really tight to each other. That's what you want. You want everything real tight. So this one it's really tight. I'm sorry, this is the negative and this is the positive input. One thing I don't like doing, but I just couldn't justify dropping a via down to bring the feedback, is putting copper underneath parts. It's not something I'm crazy about, but when you're doing a 2-layer board, there's things that are going to get kind of intermingled and stuff, and these op amps with the feedback loop and stuff is one of those things. It's one of the things I'm not crazy about actually with this particular op amp. I'd much rather do some different things with it, but you know what, this is an op amp I chose that's reasonably priced, that has a shutdown pin, and you've got to make these sorts of trade-off decisions. Stage 3 is almost exactly the same. I mean, here's the output, here's the negative input, the positive input. I still have this little feedback line coming up here. It's going under 2 or 3 parts. Not my favorite thing in the world. But then here's the stage 3. It's coming out these ways, interfacing with the microcontroller in a couple different places, because I'm not sure how I want to use this. I want to also offer whoever buys this some flexibility in how they use it as well. So it connects to 2 or 3 different places. The digital stuff is coming this way, going that way. You want to try and spread out your digital stuff because it has high speed edge rates, so you want to kind of give them a little bit of distance the best you can. I decided I was okay here with them being a little bit close, so that this 3.3 volts could run around here and have a little less impedance. And then the VREF is pretty standard stuff. It just comes in, comes out. Most of this top layer copper port is 3.3 volts. Notice I keep the 5 volts here really short. I mean, that's where the 5 volts comes in, and it's just right here. That's it. So most of the top layer is going to be 3.3 volts. There's a little bit of 5 volts here, and then there's the VREF through this section. And so this 3.3 volts is kind of given free range to kind of roam around in this area and kind of provide over to this side through this direction. And that has worked well for me in the past, having those sorts of, there's more loop there than what I'd like. But again, this is a 2-layer board. You got to make some trade-offs here to be able to produce things properly. Alright, let's jump over to the other layer, and I'll kind of show you what's going on here. Here's the here's the ground layer. So all of this is ground. Now this can occasionally be 5 volts. Remember, when this FET is off, it'll float up to 5 volts. There is a single point ground here still. So when this FET turns on, it hits that top copper, which ends up being a little bit of ground, and then it goes through this via, ties it into the single point ground. And so all of this ends up being 3.3 volts. It's all copper except for these 6 holes and these holes here. I mean, it is very low impedance, and that's what you want. You don't want to put any discontinuities in your current paths that you can. So having low impedance is critical in those applications. And what helps that a lot is having your circuits in little blocks like this. Little blocks. Always think in little blocks. Here's a block. 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 And so if you can have a good ground area, then it'll provide real low impedance for that. And so the higher speed, the more low impedance you need. So this becomes very, very critical. And in real high speed applications, which this isn't particularly a real high speed application, edge rates are probably around 100 to 200 megahertz, something like that. Another thing I want to point out is I did leave a lot of dead space here, and that's so I can keep the antenna away from any of the other booster packs and launch pads that it's connected to. And so you have a connection here with your antenna, and you can place your antenna lengthwise here and kind of keep it up off of the digital high-speed stuff that's going on around it. So I'm going to finish up some silk screening on this, and I'm going to start working on getting the board produced and ordering parts and getting those sorts of things in. I'm going to use Osh Park for this, use their 2-layer 2-week service, in case anybody's interested. And I'll get 3 boards, and that's usually enough to do at least the first prototype build, and usually the second prototype build as well. And then you can go into some low volume production, and then eventually some higher volume production. My experience is low volume, for me anyway, has been about 100 pieces, and then high volume has been around 1,000. So anyway, you just grow it slowly and get it going. You can also do it quickly, but there's trade-offs you make there. Let's just say that. Alright, so I think that's all I got. Thanks for watching. Peace.